combined loading is the lesson for today, and also the last lesson for mechanics of material. And as you can see in the real life, a structural member not only exposed to one single load, but in multiple load. Let I give you one example here. If we have a column, then when the column, typically they have a actual load P going down to that column, but as you can see that not only the one load that apply to the column, it can be the wind applied to all of that, and that create multiple time of stretches at any point on that column. And that's the topic we do today, which is how we combine all stresses with multiple load applied at any point on a structural member. So before we practice the problem with combined loading, torsion, normal forces, bending moment, transverse shears, all of that, I want you to make a summary of the elastic stress equation that we have learned for the whole semester of this class. So let's write down here. We have a elastic stress equation. Again, this is nothing new. We already learned that throughout the semester, but try to summarize what do we have. So stress created by the internal forces, and that internal force from different kind of loads. So let's start with the first column is time of load, and then the load it can create normal stress. Normal stress can be the direction sigma x, or it can be sigma y. It can be transverse shear stress. And with that, what is the 2D state of stress that we can visualize the stress at any point given the load applied. So 2D state of stress. So from that one, we have 1, 2, 3, 4, 5 column. And the first load that we investigate in this class is basically the actual load, like cow member, actual. And for the actual load, I give one example here. You have a member, and the load is applied. It can be create a tension or compression on the member, the load P, along the longitudinal axis. And if you already know, if not, go back to the first two lessons. We know it will create the normal stress along the longitudinal axis. In that case, we call it sigma x, and that equal to the load, the internal normal force divided by the areas, and the x-axis is along the longitudinal, and that the only stress that they created for the actual load. And in this case, we don't have the normal stress in the y direction and no shear stress due to the actual load. And the state of stress is very simple with 1 point on that body. Then we have sigma x and opposite sigma x. So that is the first load that we go into have, and that is very first few lesson of the class. And then the second type of load that we also investigate is the single pressure vessels. So that is single pressure vessels, and it can be cylindrical, TWPV, or spherical. Let me put the one with cylindrical here. And as you can see, the at any given point we have the hoop stress and we have the longitudinal stress. And for that one, the longitudinal stress is along the axis of the longitudinal axis, as you can see there. And the longitudinal stress, sigma L, it also actually sigma x. Let's go reversed. Sigma x along the x-axis, it's actually the equation, we call that a longitudinal axis, and also sigma 2, and it equal to PR over 2T. PRI over 2T. To be specific, RI the inner radius of the tank. And the sigma y, also sigma 1, is equal to the hoop stress, and that equal to PI over T, the thickness of the gore. And of course, that one, it poorly create the normal stress, so they don't have a shear stress. And for that one, the 2D state of stress, it would be we have sigma x, also longitudinal stress, or sigma 2, and then we have hoop stress, also the sigma y or sigma 1 that we learned previously. So that is the single pressure vessel. The next one that we want to review is the torsion. What happened is torsion. So torsion is a moment or the torque, and that make a twist about the longitudinal axis. So with that torsion, let me put down a shaft here. And in this class, if the torsion, we only deal with the circular cross section. It can be solid circular cross section or hollow circular cross section. So the torque is T, torsion T. And of course, if you understand correctly, the torsion does not create the normal stress in any x or y direction, but it creates the shear stress tangential or on the cross section, and that shear stress tau xy equal to T rho over J, 0 over J. And rho is the radial distance, J is a polar moments of inertia, T is torsion. And for that one here, the 2D state of stress is only no normal stress, so we can have E tau xy, tau xy, tau xy, and no normal stress. In the last one that we want to review is the flexure, which is create the internal bending moment on the member. So with that one here, we have flexure, and with the flexure, we can have, internal bending moment and the shear on that member. So let's put the member like a beam, and we have a distributed load or couple moment or concentrated load. Okay, so that we have that here. So it will create both. It will create both internal shears and also internal bending moment. For the internal bending moment, it will create the normal stress along the x-axis. So it's sigma x equal to my over I, and we'll get maximum at the outermost fiber for the normal stress. Sigma y, if it moment about y, so it only create in if moment about x, then it only create the stress about x. So in this case, we don't have the normal stress about the y-axis. And then, so when we say x, the x-axis is here, then with normal stress about the x-axis, so along the longitudinal axis of the beam. And the internal shear force will create the transverse shear stress, and the tau xy is equal to VQ over IT. So as you can see, the torsion also create the shear stress, and that is T rho over J, and internal shear force V, it create a transverse shear stress, and Txy VQ over IT. And as you can see, it will be the maximum, if you recall, at the neutral axis and minimum at the outermost fiber. While the normal stress due to internal bending is maximum at outermost fiber, 0 at neutral axis. And what is the 2D state of stress look like? So they have sigma x, sigma y, sigma x and tau xy. So we have here sigma x and tau xy. So we have that is tau shear stress. So that is tau xy and no sigma y, as you can see there. So that is the elastic equation, stress equation for different kind of load that we learn. And keep in mind, the last one, flexure, it creates both internal shear force and create the associated transverse shear stress as shown. And then it also create the internal bending moment that will make a normal stress sigma x in that members. So with that, as you can see, multiple load we apply, and each load may create different kind of stresses. Normal stress can be any direction, sigma x, sigma y, or the shear stress. So